Hello, welcome to APL 360. My name is Jamie. This video is part of my series on the APL 360 programming language. This episode is Basics 2. In this episode, I'm going to cover function definition. I'm going to open up the APL 360 user's manual here. I'm on page 66, which begins the section on defining functions, and just go through some simple definitions before I jump into the terminal and continue on with the tutorial from the appendix. So this is a basic definition for computing a couple properties of a sphere. So the function definition opens with the del symbol, which is shift of the letter G, and then the name of the function here is sphere. This function does not take in any arguments, and it does not produce any values. So this is just essentially using the name sphere to define some code that will be executed in a straight line manner. So what does this function do? Well, it sets a global variable surf to be the surface area, and this is the surface area computation of the sphere, but it needs to have a global variable r that's already been previously defined as the radius before this function is executed. And then this will, again, we'll be setting surf and vol. We see that the line numbers, when we're in the function editor, each line will have a particular line number. And then the function is closed by putting del on a line all by itself. Okay, so move forward here. Here's some examples of the execution of sphere. So the definition has been entered, and then the variable r is getting 2. At this point, if we were to try to access that global variable surf that's inside the body of the function, there is no value. It does not contain any value yet because the function has not been executed. So there's a value error that is raised. If the function sphere is executed, then the global variables surf and vol are set, and the values contained in them can be displayed. To compute new quantities for surface area and volume for a new sphere, the variable r needs to be set to a new value. In this case, it's being set to 1. The sphere program is being run again, and then surf and vol have new values. So we'll see in the next example the use of branching. So this can be a little confusing. Statements in a function are normally executed in the order indicated by the statement numbers, and execution terminates at the end of the last statement. So that's the normal order. But the normal order can be modified by branches, and a branch expression starts with a right arrow, and then if there's a number immediately following it, that's jumping to a particular line number. Lines can also be given labels such as L1 colon and then followed by the definition of that line, and then L1 will be a label that contains the line number, and then later if you wanted to jump back to L1, you could just use the label do right arrow L1 instead of using a particular line number that's explicit like the 4 here. It says the arrow may be followed by an expression which, to be effective, must evaluate to an integer. So that's where we can, instead of using an explicit line number, we can in essence have some code that will do some checking to see if the branch should be taken or not. And so we'll see how that's done in a moment. So if the integer lies outside the range of the statement numbers of the body of the function, then the branch ends the execution of the function. If the value of the expression to the right of a branch arrow is a non-empty vector, the branch is determined by its first component. If the vector is empty, that is of 0 dimension, the branch is vacuous, and the normal sequence is followed. So here are 3 examples of writing the function sum for determining s as the sum of the first n integers. So here we're defining sum. It's going to set a global variable s and a global variable I, and then it will determine whether it's going to take the branch to line 4 or not based on this conditional expression to the right. So we have 4 times the result of I is less than or equal to n. So if that's true, then we will jump to line 4 because 4 times 1 is 4. But if I is not less than or equal to n, then that produces a 0, and then we get a jump to 0. If you jump to line 0, which in essence, although we don't see it here in the line numbers, the header would have a 0 next to that. If we wanted to ever edit the header, we could edit line 0. But jumping to line 0 jumps out of the function and ends the execution. So then the calculation continues. So if the branch is not so if the branch is to 4, that's just the next line. So the execution continues here with line 4. If the branch is taken, then s gets s plus I gets incremented by 1, and then there is an unconditional branch to line 3. So there is a loop that's created here by these branches, and that will starting with the integer 1 up through the integer n will calculate the sum. So this function sum, again, it does not take in any arguments, and it does not produce any results. So the arguments, in fact, are just coming from, if it had arguments, they are s and I, but those are just coming from global variables that are being assigned here. And then n, we're referring to a global variable n, which is the number that we want to compute the sum up to. So it's being referred to here. And then the output is being stored in variable s. So we'll see an example after the definition has been closed. N is set to 1. The sum function, the sum program is run here. And then to see the result, we have to look at what's inside the variable s, which contains 1. So in the next case, n is assigned to 2, and so we get the sum of 2 and 1. And so when we look at s here, it contains 3. And then for 5, the sum is 15. So here is another version of sum that's equivalent in what it produces, but its operation is a little bit different. There's a different branch here in line 3. So this is jump to 0, or if this expression over here on the right, if that evaluates, it's evaluating to a vector because we have the iota here. So iota of 0 produces the empty vector. Iota of 1 produces a vector that contains only the number 1. Iota of 2 produces a vector that contains the number 1 followed by the number 2, and so on. So what happens is this I is greater than n is evaluated. If that produces 0, then we get, in essence, we get the 0 vector over here on the right. So we're jumping to an empty vector, which means just fall through the branch. So don't branch anywhere, just continue on with the operation. Otherwise, if what is on the right-hand side is a non-empty vector, then it jumps to the the line, well, it takes the first item that's in that vector and does the computation with it. So we get 0 times 1 in this case if I is greater than n. So that's in essence the number 0, which is jumping to out. So again, this is can be confusing because we're working with a number 0 and we're working with an empty vector. And the behavior of whatever is to the right of the right arrow, the behavior does two different things. In this case, whether it's a 0 or it could be another line number, it could be a 1, 2, 3, and so on. Or it could be a vector. If you're jumping to an empty vector, then that means don't branch at all, just continue on with the straight line execution. If you're jumping to 0, it means essentially in the program, jump out, or it could be jumping to a particular line number, which would jump to that particular line. So this will, if I is greater than n, which means that internal index, you've reached the particular integer that you're counting up to. So if that's true, then this becomes 1. So we get 0 times 1 is 0. So in essence, jump out of the program because you're done at that point. Otherwise, continue on with the loop. S gets S plus I gets I plus 1, and then jump to 3, do the check again, and continue. In this next example, the branch has been moved down to the bottom. So S is being set to 0 initially, I is being set to 0, S gets S plus I is being incremented here, and then it's jumped to 3 or fall through. So in this case, if I is less than or equal to n, then that would be a 1. Then we're multiplying 3 by iota of 1, which would give us 3 times 1, which is 3. So we would jump to 3. If I is not less than or equal to n, then this becomes a 0. So iota of 0 is that empty vector, and that means continue on with the execution, but that moves from line 5 to line 6. Line 6 is the end of the program, and so it's done. It just falls through and out at that point. So this is an important statement that can be easy to miss since it comes at the bottom of this page, where we're thinking about all of these intricate details. This is from the last two functions in the foregoing example. It should be clear that the expression, the times followed by iota occurring in a branch, may often be read as if. So for example, jump to line 3 times iota I less than or equal to n may be read as branch to 3 if I is less than or equal to n. So that's an important idiom, a common idiom that you will see in APL 360 functional code. So then the next section talks about the difference between local and global variables. We've only seen up above referencing global variables and setting global variables, but there are times, and I would say it's better programming practice, that if you do not need things to be set globally, if I need an internal index, I want that index, in this case I, to be a local variable. So we use a semicolon followed by a variable, and we could have several of these. You could follow I with a semicolon and then have another variable, maybe j, and so on. These variables following semicolons will be treated locally inside the body of function definitions. So in this case, for sum 3 has been defined, it's been run. I was, before it was run, I was set to 20, and then after the function is run, the value of I is examined and it still contains 20, although I internally is being set to different values. We can see what happens if we do not put I as a local variable in the definition on the right. You'll notice it's missing from the header. And then we set I to 20 when we run the program and we examine the value of I, and it contains 6. Okay, so moving on. So I would say most of the time that we're writing functions, we want to refer to explicit arguments rather than relying on arguments that, well, essentially variables that have been globally defined in our calculation. So here, if we want to calculate the surface area of a sphere, we're going to define a function. The function name here is sphere, and it's taking one argument, and that is given the parameter name x here. So then in the definition, we're going to refer to that parameter. It's going to take the place of the radius of the sphere that we're calculating the surface area for. And so then when we compute the value of sphere 2, then we'll need to examine this global variable sur for surface area to see what the surface area is. But we didn't have to define the variable r outside of the function body before we ran the function. So to see another surface area, all we have to do is run the same program, SPH, or the same function, with a different argument, 1 in this case, and then examine sur again, and then we'll see that it contains a different value. Now, I would say that probably even more common than that form is not only having the explicit argument, but also having an explicit result. So I want the function sphere to actually produce the value of the surface area instead of setting this global variable sur, and then that needing to be examined to see the value. So how can we do that? Well, in the function header, we right after the del, we put in a return variable. So here there's essentially a throwaway variable, z gets, and then we have the name of the function, sp in this case, and then it's taking one argument, x. And then we set the result of the calculation, and we set that throwaway variable z to that result. And this will go ahead and return the value of the calculation, and z will not have been defined globally. It's in essence acting like a local variable here. So here's a calculation of taking SP1 and multiplying it by 3. Because it's actually producing a value, we can set that to Q, or we can just run it like this and see the result printed in the terminal window. So they've set that to the variable Q, and then they've examined it. Here they're using a global variable r, and then passing in r as an argument into the calculation. So calculating the surface area, multiplying by r again, and then dividing by 3 to get this new quantity. All right, so with all of that kind of the basics of how there are different ways of defining functions, let's see just the mechanism of jumping into the function editor and using it, making some mistakes, making some corrections, and so on in a terminal window. So I'm going to move forward to page 118, and let's say I'm going to go earlier than that. So let's see, at the end, we finished the last video at 116, so I'm here at the top of page 117. I'm going to move this out of the way and then bring the terminal window up to the front here. Okay. I've just quickly defined a Hello World program. I don't think I've done this before. In APL, it's really simple. We just write out the character constant here for Hello World with the single quotes, the beginning and end, and we get Hello World being printed there. So I'm going to define a function here, f, which will use an explicit, which uses two explicit arguments and will have an explicit return value. So I'll do del z gets. The left argument will be x, the function name will be f, and the right argument will be y. So this is a dyadic function. Enter, there's the header. Essentially that's on line 0. So now I'm put on line 1. I'm in the editor now, a type of line editor for the function definition. So now I'll do the calculation. We'll say z gets left paren, x raised to the power of 2, right paren plus y raised to the power of 2, right paren, and all of this raised to the power of 0.5, which is the square root. Then I'll close the definition. So function f, you've probably recognized the calculation here. We're taking x squared plus y squared and then taking the square root of all that. This is the length of a hypotenuse of a right triangle with one side x and the other side y. So we can do a quick calculation. 3f4. This is should be a 3, 4, 5 right triangle, and we get the 5 being produced there. So we'll see in the next couple of lines, not providing explicit numbers as the input to f, but we'll use a variable and even calculated numbers for that. And then we can, because this is providing an explicit return value, we can set that to, we can set a variable to that return value as well. So p gets 7. And then we're going to set the result. Q gets, then for x, we'll do the quantity p plus 1. So that's on the left-hand side. I used the wrong bracket there, so I will backspace and line feed, use a right parenthesis, so that's on the left. And then although we don't need to put in a space here, I like to, for symmetry, I like to put in a space before and after the function names. And then p minus 1. So we've got p plus 1, f, and then p minus 1. So this is being set to the variable q, and then when we see what's contained in q, we get 10. So this was essentially an 8 by 6 triangle, and then again, like a 3, 4, 5, another one that works out evenly would be doubling those values. So we've got 6, 8, 10. 10 is the hypotenuse there. Now let's see what happens if we leave out those parentheses to the left of f. So just a reminder of the order of operations here. So we'll put 4 times 3 f4. So you might think that this looks like we have one side of the triangle would be 12, and then the other side of the triangle would be 4, and then we're going to compute the hypotenuse. But that's not the way this calculation is done. Remember, it's done in APL from the right back to the left. So we've got 4f3, so that will go ahead and be computed as 5, and then 5 times 4 will be 20. So we get 20 as the result. Now we're going to define another function here that will be the signum function. We'll say del b, that's our return value, gets GA. So the function name is G. It takes one argument, in this case, A. And in the function definition, B gets, and then this is a famous one-liner in APL for calculating the sign of a number, where you get 1 if it's positive, 0 if it's 0, and -1 if the number is negative. So it looks like this. We've got a greater than 0 minus a less than 0. And close. So g of 4 will give us a positive 1. G of -6 will give us -1. We can set a variable x to be -6 and then do g of x, and we see the sign even of the number that's contained in the variable. Here's -1. And just quickly to demonstrate that we do get the expected answer for 0, we see that there also. The next one, we're going to define a function h, which will be like g, but there will be no explicit result. So we'll do del h of a. So notice that we're not putting any kind of dummy variable and a left arrow inside the header. So here, to get the return value, we need to set that answer to some global variable inside. So we will set that here to p. P gets then the same calculation as above. A greater than 0 minus a less than 0. And then close the definition. We can do h of -6, and then we don't see the result because there was no explicit result inside our definition. We have to look at what's now contained in the global variable p to see the answer there. And we can do this again with another number like h9 and look at p, and we see p is 1. Now if we try to set a variable like y gets the result of h applied to 9, we'll see that won't work because the function h is not producing an explicit result. So we get a value error because you cannot assign, I can't say assign y and then press enter. That's a syntax error, but above, it's essentially trying to assign nothing to y, and so you get a value error in that case. So that's, to me, is one of the benefits of defining a function with the explicit result, is that then that function, in this case g, could be used in another computation, or you can set a variable equal to the result of using function g, applying function g. Whereas when you don't have it provide an explicit result, you can run into these kinds of errors. Okay, the next function we'll define is the factorial function. So we're going to use an explicit result here. Del z gets factorial of n. And then we're going to use an internal local variable. So I'm going to use semicolon here, followed by the name of that internal variable I, or local variable. Okay, so z gets 1. I gets 0. Now I'm going to use a label for line 3. We'll use the label L1 followed by a colon. That's the shift of the period. So line 3, or L1, in essence here means 3, but we'll be able to refer to this in a branch later as L1. So on this line 3, I gets I plus 1. So increment I. Now we do a conditional branch. So this is a right arrow, 0 times iota. Again, that's going to be a really familiar idiom. 0 times iota, which is shift I, if I is greater than n. So I greater than n. So again, we can read this times iota as if. So jump to 0 if I is greater than n. So that means we've completed the computation. Our internal index has reached above the number that we wanted the factorial for. So let's say we want the factorial of 5. So we start by multiplying, well, we will get to the multiplication part in just a second, but I is starting at 0, so then I is incremented. I will be 1. Then we'll multiply 1 by, we want 1 times 2 times 3 times 4 times 5. And then we jump back up to this label. On the next iteration, I will be 6. So when 6 is greater than the number 5 that we wanted the factorial for, we are done. So we want to jump to line number 0 in that case. Now, if I is not less than n, then we get iota of 0, which is the empty vector, and then trying to jump to an empty vector does no jump at all. We'll just continue executing with the line after this one. So line 5, then we do the multiplication. Z gets C times I. And then we need to we need to loop back around. So we have to be careful where we loop back around. We don't want to loop back to line 1, which resets Z to 1. We don't want to loop back to line 2, which is setting I to 0. We want to jump back to L1, which is going to do the increment, check to see if we're done or not. If we are done, jump out of the program. If we're not done, go ahead and do another multiplication, and so on. So how do we do that? This branch, it is an unconditional branch to label L1. And again, we didn't, in a short program like this, we didn't even need to necessarily even use a label. Labels are really useful, though, in longer programs where you may have to come in and interpolate some other lines in between existing line numbers, and you wouldn't want to have to go in and renumber all of your branch points. So labels are really useful for that. And then I'm going to close the function definition. Factorial of 3 is 6. The factorial of 5 is 120. Now there is a trace function or a trace operation that's built into APL where you can set traces of particular lines in your function, and we'll see that syntax here of how you turn that on and then turn it off. So we'll do a T with a delta symbol, which is Shift H. And so that's trace of factorial gets, and then the line numbers that we want to see the values of. So at line 3 and line 5. So that's turning on the trace operation. Now we run the function. We're going to set x gets factorial of 3. And then we see the first time through on line 3, I is 1. On line 5, Z is 1. Then the next time through, I is 2. Z is 2. The next time through, I is 3. Z is 6. Then the last time through, I is 4. So again, that's that line we're checking, is I greater than n. So 4 is greater than 3, and then we jump out of the program, so we never reach line 5 again at that point. Now to reset the trace control, we do T delta, and then the name of the function gets 0, and that will turn the trace mechanism off. Okay, at this point, I'm going to go ahead and stop this video. I will continue in the next video, basics 3 with more function definition and more editing, function line numbers. I think this video has probably gone on long enough for this episode, and so I hope to see you again in the next one.